Hello everyone, my name is Tongtong Yan and I'm from Shanghai Jiao Tong University. My topic is about the chemical effects of ammonia addition on soot formation and evolution in laminar and turbulent flames. First is the background. We all know that combustion process for hydrocarbon fuels will generate a lot of soot. How to minimizing the negative effects of emissions is a crucial task. One common strategy is to reduce carbon emissions is to apply carbon-free ammonia fuel for combustion process. However, due to its low laminar flammability, high NOx emission and low laminar flame speed and narrow flammability, burning ammonia in the existing combustion devices still face some challenges. Another feasible way is to co-firing ammonia with hydrocarbon fuels. Various experimental studies observed strong suppression effects in ammonia-duped flames, whether in laminar or turbulent flames. So in our study, we want to first develop a solver can describe the soot distribution in both laminar and turbulent flames, then study the chemical effects of ammonia addition on soot formation. Here is the methodology. First, to simulate soot in laminar flames, we first developed a solver to handle finite rate chemistry case. In this case, it transports all the species mass fraction equations. The transport equations for mass, momentum, species, and energy are solved using open form. For the finite rate chemistry case, Cantero is coupled with open form to manage molecular transport and detailed chemistry reactions. For the soot part, the method of moments is used, and the transport equations of moments instead of the number density functions of soot particles are solved. To close the soot source term, the hybrid method of moments is used, and the M00, M10, M01, and the number density of the smallest particle N0 are transported. And here is the detail for the soot source term. First, pH dimers collide and lead to the formation of the first soot particle. This process is called nucleation, and the condensation results from the collision of a soot particle with a pH dimer, and coagulation is the collision of two soot particles. Surface growth results from the addition of carbon atoms on the surface of soot particles through Hacker mechanism. While soot particles are oxidized by both hydroxyl radicals and oxygen molecules, and then the internal structure has been weakened and large aggregates break apart into small pieces. This process is called fragmentation. We can see that these source terms are related to the relevant species concentration and the reaction rate. Although the first solver, the finite rate chemistry solver, can well capture the soot evolution process in certain reacting flows, the selected chemical mechanisms may contain a large amount of species. Solving such a big number of equations would be computationally demanding, especially in turbulent flames. To efficiently describe the thermochemical properties of flames, various methods have been developed. One is the flame-lit progress variable solver, FPV, and this is a low manifold method. This method skips the complex chemistry process by constructing certain map relationships between key parameters and other variables. By using this method, we only need 4 key parameters: the mixed fraction, the variance of mixed fraction, the progress variable C, and the heat loss H, to construct a 4-dimensional table. And in the simulation process, we only need to transport these 4 parameters, and through looking up the table, we can get other information, such as the source term in this equation. These source terms in the equation. And since gas phase pH have relatively slow kinetics, it can't immediately adjust to the rapidly changing scalar dissipation field, so they are lumped their lumped mass fraction is obtained from a transport equation. This method makes solving for soot in turbulent flows more efficient than finite rate chemistry solver. And for the soot moment source term, we don't need to calculate the source or reaction rate according to pH concentrations. Instead, we can directly look up these parameters based on these four values. And then we can get the data we need to calculate source term, such as the temperature, the dimerization rate, surface growth rate, and the other parameters we need in these source terms. And here is the solver validation. This is a counterflow diffusion flames, and the cycle here is the results from the experiment data, and the solid lines are the results by using our solvers. We can see that this solver can both well predict the soot volume fraction and the particle diameters. And first, we use the solver to simulate the chemical effects of ammonia addition in a laminar flame. Here is the flame settings. This is a counterflow flames, and the experiment data is from Bennett. And we can see that we use 3 different ammonia ratios, and then use 4 different mechanisms we developed to explore the chemical effects of ammonia addition on soot flames. And here is the mesh settings. And this is the 4 mechanisms we developed. First is the dominant mechanism KM2. This is a mechanism about hydrocarbon fields. And first, we combine it with the donor ammonia mechanism 1 to generate a new mechanism called MC0 mechanism. We can see that in this mechanism, there are no interactions between hydrocarbon species and nitrogen-containing species. Then we incorporate the dominant mechanism with other donor mechanism 2 and generate MC2 mechanism. In this mechanism, it contains the interactions between nitrogen-containing species and C1 and C2 level hydrocarbon species. Based on our simulation results, and within based on this MC2 mechanism, we add some reactions related to benzene and amino, and generate the third mechanism, MC2 aniline mechanism. And we found that this mechanism is also can't well predict the results. So finally, based on our soot-based global pathway analysis, when we then add a reaction involve relate to C9H7 and generate the final mechanism. The detail about this 4 mechanism will be discussed later. And here is the outline of our studies. First, we compile the MC0 and the MC2 simulation results. Because the MC2 mechanism contains the C1, C2 hydrocarbons and the nitrogen-containing species interactions. So based on this, we can compare the impact of these interactions. Here is the results. First is the soot volume fraction predicted by MC0 and MC2. This is the measured data, and we can see that both MC0 and MC2 can well predict the case without ammonia addition. However, with the ammonia addition increasing, the measured soot volume decreased significantly. You can see here it decreased significantly. However, the simulation results for MC0 only shows a very slight reduction, and the MC2 mechanism is better than MC0, but it also shows a very slight reduction. These results indicate that when ignoring the interactions between all hydrocarbon species with nitrogen-containing species, the suppression effects of ammonia addition on soot formation can't be well reproduced. But even we consider the C2 level interactions, the inhibitory effect of ammonia is still significantly underestimated. And here is the results for some species and the Soot source term. Since most of the previous studies think ammonia addition leads to acetylene suppression and thus Soot volume fraction reduction, we first plot the concentration of acetylene. Simulation results suggest the concentration of C2 H2 remains relatively constant as ammonia concentration increases. This means that the presence of ammonia has a little impact on this species. So we think that the decreasing in the surface growth source term may attribute only to the reduction of the Soot volume fraction. And these 4 pictures is about the 4 different source terms. We can see that for the condensation source term, the magnitude is quite larger than the other 3 terms, and we can see that the condensation is the most dominant source term in this case. As shown in the previous slides, although the suppression effects of MC2 is better than MC0, the effects are still significantly underestimated. So due to the reaction between benzene and amino is suggested to be important in some studies, we then generate the third mechanism called MC2 analyte. And we incorporate some reactions involving these 2 species into the chemical mechanism. And here is the results for the Soot volume fraction. We can see that compared with MC2, the formation of analyte suppresses the formation of Soot. However, the inhibitory effect is not notably. Since this mechanism introduced some reactions related to benzene, so we show the variation of A1 here. We can see that the mole fraction of A1 at different concentrations of ammonia is not very different in both simulation and experiment. And for pH with 2 to 3 rings, it also shows a little difference with ammonia addition. The results from the 3 different mechanisms we tried indicate that the existing theories fail to predict the notable decrease in Soot volume fraction when ammonia is duped with counterflow flames. So we then do a Soot-based global pathway analysis, SGPA. This method introduces element flux analysis from pH to Soot-based global from pH to Soot based on the global pathway analysis. And it can reveal the most dominant global pathways for Soot formation and evolution. Here is the results for the global pathway analysis. We can see that these different pathways represent different chemical routes from the initial reactants to final products at different locations. You can see from this picture, although the specific global pathway may differ with different ammonia concentration, GP2, the blue circle, is always emerges as the dominant path near the peak of Soot formation. So we think that the reactions involving C9H7 to Soot is a pivotal step. Based on this analysis, we then incorporate reactions involving C9H7 and amino into the mechanism, and develop a tentative mechanism because the coefficient of this reaction is adopted from this reaction by analogy. It's just a tentative mechanism. And here is the results for the Soot volume fraction. We can see that the prediction results of this, the final mechanism is better than the previous one, and the inhibitory effect of ammonia addition is notably. Here we also show some key species such as C97, A2R5, and the 4-ring pH, and these all decrease with the addition of ammonia. Finally, is our conclusions. We can see that we use the solver we developed and to first study the effect of chemical effects. Study the chemical effects of ammonia addition on counterflow flame. We use 4 different mechanisms and find that the final mechanism we developed can well predict this trend. And in our future work, we will study the chemical effects of ammonia addition on turbulent flame behavior. Thank you.